So in the last period, we have studied about the hydrogen, its occurrence, and various isotopes and various hydrides of hydrogen. Let us revise some of the knowledge by solving some of the problems or questions uh, from that portion. Let's solve one problem. The problem is as such. Would you expect the hydrides of nitrogen, oxygen and fluorine to have lower boiling points than the hydrides of their subsequent members? Give reason. Now, first of all, we need to know about this nitrogen, oxygen and fluorine. So nitrogen belongs to group number 15, this is 16 and this is 17. So if you look into the group number 15, you have nitrogen, phosphorus, arsenic, antimony and bismuth. If you look into group number 16, you have oxygen, sulfur, selenium, tellurium and polonium. And if you look into the halogens, you have fluorine, chlorine, bromine, iodine and astatine. These are the elements. Now these are called the subsequent elements. In the question, what they have asked is their subsequent group members. So these are the subsequent group members. Now we know that hydrogen bond is possible only with these three elements, which are the most electronegative element, and they are nitrogen, oxygen and fluorine. So the other elements, they will not make hydrogen bondings. And we know that when there is hydrogen bonding, the melting and boiling points of that particular compound increases. So thus, when this nitrogen, oxygen and fluorine are available, there will be hydrogen bonding, and due to the hydrogen bonding, they will have higher melting and boiling point as compared to those elements which are formed, or those hydrides which are formed by the subsequent elements, and they do not have hydrogen bonding, and that is why they do not have higher melting on boiling point. So this is how, my dear students, you understand or you can answer the question. So now if you read the question once again, please have a read it to once. Would you expect the hydrides of nitrogen, oxygen, and fluorine to have lower boiling point than the hydrides of their subsequent members? No. The answer is quite simple, no. On the basis of the molecular masses of NH3, H2O and HF, their boiling points are expected to be lower than those of the subsequent members of hydrides. So if you look into their molecular mass, yes, you will feel that yes, they will have the lower melting point and boiling point. However, due to the higher electronegativity of nitrogen, oxygen and fluorine, the magnitude of hydrogen bonding in their hydrides will be quite appreciable. Hence, the boiling point of ammonia, water and hydrogen fluoride will be higher than the hydrides of their subsequent group members. Now we have the next question. Can phosphorus with outer electronic configuration 3s2, 3p3 can form pH5? So if you look into the electronic configuration 3s2, 3p3, it has 5 valence electrons. And thus, if phosphorus loses its 5 valence electron, it turns out to be p plus 5 and, and 5 electron. So thus we can easily expect the phosphorus to make pH5, which is an hydride, like phosphorus can make PCl5. So phosphorus can make PCl5, which is a stable compound. But here the question is, can phosphorus make pH5? That is the question. Let us answer these questions in a better manner. Although phosphorus exhibit +3 and +5 oxidation state, it cannot form pH5. Why does it cannot form pH5? Because this can be explained due to the high enthalpy of atomization and high value of electron gain for phosphorus that does not form pH5 with hydrogen in its highest oxidation state. So please remember that phosphorus has got high electron gain enthalpy, and for the value of electron gain for phosphorus, due to the high value of electron gain for phosphorus, the phosphorus cannot make pH 5, or phosphorus cannot make pentahydrate with hydrogen. So this is the question of knowledge. Please remember it. You need to remember that phosphorus cannot make pH 5 because the high enthalpy of atomization and high value of electron gain, phosphorus cannot make pH 5. So please remember these answers. There is no logic to understand, but you just need to remember the condition of our phosphorus. Now we want to study a very important compound of hydrogen, which is known as water. Water, a major part of all living organisms. So water is a major part of all the living organisms. That is what we are well aware. Human body has almost 65% water. Some plants may have 95% of water. Water is crucial for our life, and water is a solvent of great importance. We will study why it is a solvent of great importance. Now, distribution of water into the various parts. So it is in ocean, the water is 97.33%. In saline lakes and inland seas, the water is 0.0. Like total, if we consider the total 100% water of on the earth, out of this 100%, 97.33% is present in the ocean. 0.008% is present into the saline lakes and inland seas. 2.04% is present into the polar ice and glaciers. 0.61% of water is present into the groundwater. 0.009% water is present into the lakes. 0.005% of water is present in the soil as a moisture. 0.001% water is present as an atmospheric vapor, which we call it as a moisture. And 0.0001% of water is present into the rivers. So whatever the water we can see into the rivers is a very small quantity of water. Now let us understand the various physical properties of water. Water is a colorless, tasteless liquid. Due to hydrogen bonding, water has hydrogen extensive bonding, and that is why these properties of water are found very high. Which are those properties? You can see that it has got very high freezing point as compared to the other element. As compared to the other hydride, water has got very high freezing point, very high melting point. We have seen due to hydrogen bonding. It has the volume. See, water is a liquid. But if you look into the H2S, H2SE, H2TE, they are the member of the same group. If you go down the group, actually atomic mass increases. So instead of, if this is liquid, then they should be found in solid state. But inverse to that, this hydrogen H2S is a gas very well known to us. So due to the hydrogen bonding, water is liquid, whereas H2S, H2TE and H2SE, all these are the gases. So please remember that in comparison with all these compounds, water has got high freezing point, high melting point, high boiling point, high heat of vaporization, high heat of fusion as compared to the H2S and H2SE. As compared to the other liquids, my dear students, water has high specific heat. High specific heat means it requires more energy to be converted 1 kilogram of water liquid to 1 kilogram of water vapor. It has got very high thermal conductivity, it has got very high surface tensions, it has got very high dipole moment, and it has got very high dielectric constant. Please remember, this dielectric constant very high is responsible for water to break down the polar molecules into the ions. Generally the ionic compounds, they have ions, but the non-ionic compounds or polar compounds, they do not have ions. But this water makes these polar compounds even to break into the ions, and that is what it is, the process which is known as the ionization. So please remember that water has got very high dielectric constant, and that is why it can ionizes those covalent compounds which are polar in nature. These properties allows water these properties allow water to play a key role in the biosphere. High heat of vaporization and high heat of heat capacity are responsible for the moderation of climate. So we can see the moderation of climate, we can see the winter season, we can see the summer season, we can see the rainy season, we can sometimes see the suddenly climate changes and we can get cloudy atmosphere. All this is possible because of the high heat of vaporization and high heat capacity of water. We can see the various moderation into the climate change. Moderation of body temperature is also responsible due to these properties of water which are known as the high heat of vaporization and high heat capacity. It is an excellent solvent. Please remember water is an excellent solvent. For the it is an excellent solvent for the transpiration ions and molecules required for plant and animals metabolism. So it is a wonderful solvent for all the reactions that takes place into the plants. Due to hydrogen bonding, please remember my dear students, due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates, please remember these alcohols and carbohydrates are purely covalent compounds. All the bonds present in alcohol and carbohydrates are covalent, but still they are very well dissolved in water. These alcohol and carbohydrates, they are, when we talk about alcohol, alcohols are soluble in water in all proportions, especially the ethanol and methanol. So this is how, my dear students, we understand the various properties of water that makes it a very good or universal solvent. Now, dear students, we want to study about the structure of water. Though we have studied into the chemical bonding chapter, let us revise it. In the gas phase, water is a bent molecule with the hybridization sp3 and two lone pairs. Please remember that this water has two lone pairs. And the bond angle of water is 104.5 degree. The OH bond length in water is found 95.7 picometer. So this is the structure of the band structure of water in gaseous phase. You can see the dipole in water. So hydrogen has got plus delta charge because it is less more electronegative. This hydrogen has also got plus delta charge because it is more electronegative, and that is why our oxygen has got 2 delta minus charge, and thus the water molecule is available as a dipole, and that is why it has got very high dielectric constant. If you look into the various orbitals that are present into the water, you can see that oxygen is sp3 hybridized, and by using these two orbitals, it forms the bond with our hydrogen with the bond angle 104.5 degree. And these two are the orbitals in which two lone pairs are present into the water. So here we have actually oxygen, and oxygen is bonded with the two hydrogen with the bond angle, and this is how you can understand the orbital overlap picture in water molecule. So this is the structure of water. If you could not understand anything, my dear students, you can ask. बच्चों अगर आपको कुछ समझ में नहीं आया तो आप लोग पूछ सकते हैं. Okay, then water is a highly polar molecule. You have seen that there are two delta minus charge on oxygen and delta plus charge on hydrogen. That makes water a highly polar molecule. Its orbital overlap is shown in the picture. We have just seen the orbital overlap. In liquid phase, water molecules are associated together by the hydrogen bonds. So hydrogen bonds makes these water molecules to get associated with each other. Now, my dear students, we want to study about the ice. Ice is the solid and crystalline form of water. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes into hexagonal form. Please remember that now the tetrahedral structure of water, please remember that the tetrahedral structure of water, now it turns to be hexagonal. We will see into the ice. But let me explain you first the tetrahedral structure of water. I have just explained you that we have these two, and this is the band. Here we have hydrogen and hydrogen. So this tetrahedral form, which was the bent shape, has been turned into the hexagonal shape into the ice. Even this hexagonal form is turned out to be cubic form when it comes to the very low temperature. The crystalline form of water is ice. At atmospheric pressure, it crystallizes in the hexagonal form, but at very low temperature, it converts itself into the cubic form. So please, my dear students, please pay attention and understand this hexagonal form of water. You can see here, I have tried to show you, or I have drawn a picture for you, where you can see that the green color part is your green color is your oxygen and red color is your hydrogen. So you can see that green color and red color, these water molecules, they have arranged themselves in a hexagonal form, and this hexagonal form is, you can see them, they are joining with each other with the hydrogen bonding. So these are the H bonds which are found among the water molecules, and thus they form the hydrogen bonding, and they make, you can see that this hydrogen is bonded with this hydrogen is bonded with this oxygen with the hydrogen bonding, and thus we can see the various hydrogen bonding among the water molecules, and this is how we study the structure of ice. Highly ordered, you can see here I have written highly ordered three-dimensional hydrogen bonded structure of ice. This is the highly ordered three-dimensional hydrogen bonded structure of the ice, you can see here. Now a very important point, density of ice is less than the density of water. What is the reason that density is less than the density of water? You can see that when the water molecules are arranged in the hexagonal form, you can see a large space is generated. When water is formed into the hexagonal form, you can see this large space is generated. So water, when it turns from liquid to the solid state, it forms the hexagonal shape due to the hydrogen bonding, and this takes more volume as the volume it is taken into the liquid state. Density of ice is less than the density of water, therefore an ice can float on water. In winter season, ice formed on the surface of lake. In winter season, my dear students, the ice formed on the surface of the lake provides the thermal insulation which ensures the survival of aquatic life in underwater. So my dear students, when we have lakes and oceans, their surface has got ice, but this ice does not allow the extra coldness to come inside the water, and that is why the water underneath the ice is prevented from further freezing, and thus the aquatic life in underneath this ice can survive easily even during the winter season. This is the fact. This fact is of great ecological significance, and due to this particular characteristic of water, the aquatic life under the ice can live better, and that is why this property of water is of great ecological significance. Ice has highly ordered three-dimensional hydrogen bonded structure. That is what we have seen into the picture. Examination of ice crystals with X-ray shows that each oxygen atom is surrounded by four other oxygen atoms tetrahedrally at a distance of 276 picometer. Hydrogen bonding gives ice rather an open type of structures with wide holes. I have just shown you those holes in the hexagonal structures. Due to these wide holes, volume per mole of water molecule increases and ice has lesser density than water. So if you are asked in the exam, explain why ice has lesser density than water, then you can say that in the structure of ice, when it is examined by X-ray, it was found that in the structure of ice there were wide holes. These holes makes the ice to take more volume per mole of water as compared to the more volume per mole of water taken in case of the liquid water. So in ice, one mole of water molecule take more space. Thus the volume is increased and density is decreased, and thus the density of water is more than the density of ice, or the density of ice is less than the density of water, and that is why ice floats on water. So this is how, my dear students, we understand why ice floats on water, or why the density of ice is less than the density of water. The wide holes present in the structure of ice can hold some other molecules of appreciate size interstitially. So my dear students, this is even one of the important point about ice, that we can understand that the other molecules can easily allowed to go inside the crystal of ice, because these ice crystals have a wide holes inside them, and then they can form the interstitial molecules or interstitial compounds. Let's move and understand the various chemical properties of water. Water reacts with large number of substances and shows various properties. The first property that we need to study about water is the amphoteric nature of water. Amphoteric nature means the nature of water in which the water molecule can react with both acid as well as base. That kind of nature is known as the amphoteric nature. Water has ability to act as an acid as well as base, and it behaves as an amphoteric substance. In Bronsted sense, it acts as acid, and with ammonia and with H2S it acts as a base. So my dear students, when water reacts with ammonia, it acts as an acid, and when water reacts with H2S, it acts as a base. What is what is acid? Acid that produces H plus ion. So here, my dear students, water produces H plus ion and OH minus ion. This H plus ion, when it reacts with ammonia, it gives us NH4 plus. So you can see these two are the products obtained when water reacts with ammonia. When water reacts with ammonia, a process known as protolysis takes place, and we get OH minus and NH4 plus. Same way, my dear students, when water reacts with H2S, H2S being more acidic, it produces H plus ion. So H2S produces H plus ion and HS minus ions. These H plus ions reacts with water and produces H3O plus ion. So you can see these two are the products when water reacts with H2S. When water reacts with H2S, it produces H3O plus and HS minus. So this is the way, my dear students, we can easily understand about the amphoteric nature of water. Water can react with acid as well as base. The very important process of water is known as the autoprotolysis. That means self-ionization. So one water molecule behaves as an acid and another water molecule behaves as a base, and that is why the one which behaves as an acid, it produces H plus. The one water molecule which behaves as an acid, it produces H plus. This H plus and H2O gives us the H3O plus, and from this OH minus is being produced. So this is how, my dear students, we can understand that water undergoes a process which is known as the self-ionization or autoprotolysis, and due to that we can get H3O plus and OH minus. So water can behave as well. Water can behave as an acid and base with the different compounds, or when water reacts with water, it can behave both as an acid as well as base, or one molecule of water behaves as an acid, another molecule of water behaves as a base. The second property that we need to understand about water is the redox reactions involving water. Water can be easily reduced by dihydrogen. Water can be easily reduced to dihydrogen by the various electropositive metals of group number 1 and 2. You can see that when water reacts with sodium, it produces sodium hydroxide and hydrogen gas. Even in the 10th standard, you might have studied about the production of the hydrogen gas from water by the various reactive metals. Thus, it is a great source of dihydrogen. So, water can be a great source of dihydrogen, my dear students, because when water reacts with the various metals, dihydrogen can be produced. So, there are various ways by which we can produce dihydrogen from water and use it for the various purposes, especially to resolve the problem of our energy. Water is oxidized to oxygen during the process of photosynthesis. You can see here that water reacts with carbon dioxide and turns out into the oxygen. Here, the oxygen which was in -2 oxidation state turns out to be 0 oxidation state, and thus we can say that water has been oxidized to oxygen. With fluorine also, water is oxidized to O2. You can see that when water reacts with fluorine, it produces oxygen gas, and that is how water is oxidized to O2. Next, hydrolysis reactions of water. My dear students, hydrolysis is the type of reactions in which water is separated into the H plus and OH minus ions, and then it is added to some other compound as a whole. So let us study about the hydrolysis reactions. Due to the high dielectric constant, water has a very strong hydrating tendency. It dissolves many ionic compounds and some of the covalent compounds, and some of the ionic compounds are hydrolyzed in the water. Water being H2O added as H plus and OH minus to the compounds or species, and this particular process we consider it as a hydrolysis. Let us see how does it work. You can see that we have P4O10 and 6H2O. This P4O10 turns out to be H3PO4 by the addition of water molecule into the P4O10. Remember, my dear students, that when water is added to P4O10, it is first or it is added in the form of H plus and OH minus, and that is why this process is known as hydrolysis. That you can easily understand in these next two processes. SiCl4, when it reacts with water, you can see that Si combined with O2 and Cl combined with hydrogen. So this is again the addition of hydrogen and oxygen separately into the SiCl4 elements. Same way, my dear students, when we have N-3 and we have water, water is converted into H plus and OH minus ions, and thus this H plus combines with the N-3 and we get ammonia. So this is the way by which water is being divided into the hydrogen and oxygen, or it is divided into the H plus ion and OH minus ion, and when it is added to another compound, we call this process as a hydrolysis. Now we want to understand the other process which is known as the hydrate formation. In the process of hydrate formation, my dear students, water molecule is added to the other compound and it remains intact. That means it is not broken into the hydrogen and oxygen, but it itself, a complete water molecule is being added to the other compound. Let us understand how is it possible. From the aqueous solution, many salt can be crystallized as a hydrated salt. You might have studied in 10th standard that we have CuSO4 into 5H2O. We have even studied about CaSO4 into 2H2O. Or we have even studied about CaSO4 into 1 by 2H2O, which was known as the calcium sulfate hemihydrate, which was our plaster of Paris. Even in my class, I gave the example of Na2SO4 into 10H2O. So in the 10th class itself, we have studied about the water of crystallization. So my dear students, when the crystals of the various compounds are formed during the process which is known as the crystallization, the water molecules are added to the various compounds. These water molecules are added to the various compounds in the three different forms. You can see that these are the three different forms in which these water molecules can be added to the various compounds. Look at this. These are the three various ways by which water molecule can be added. Water molecule can be added as a coordination water. You can see that in the Cr plus 3 ion, suppose you have CrCl3. So Cr plus 3 ion and 3Cl minus, in between this water molecule, this 6 water molecule per 1 molecule of CrCl3 are being added. So this is what it is known as the coordinated water. Then, my dear students, water molecule can be added as an interstitial water. So my dear students, we have interstitial water, for example, BaCl2 into 2H2O. This BaCl2 molecules, when we have, they also have the interstitial sites and in this interstitial site, water molecules are being added. So this is what it is known as the interstitial water. Same way, my dear students, we can also have water to be added as an hydrogen bonded water. So you can see that here, these four molecules of water are added as a coordinated water with the copper plus 2 ions, but this water molecule is added as a hydrogen bonded water molecule. So this is how, my dear students, we can easily understand that water can be added to the various species in a three different manners, and these three different manners are either in the form of the coordinated water, either or in the form of the interstitial water, or in the form of the hydrogen bonded water molecules. My dear students, so these are the various ways by which the water can be added into the compounds. We will understand it better by understanding this question's answer. So let us read the question. How many hydrogen bonded water molecules are associated with CuSO4 into 5H2? बच्चों हमने 10th standard में पढ़ा था कि when we have a CuSO4 into 5H2O, which was blue in color, when we heat it, it turns out to be CuSO4 and 5 water molecules are being removed. And when these 5 water molecules are removed, this CuSO4 turns out to be white in color. I will share a link with you in the group where I have done this particular experiment that you can see on the YouTube. So what we can see that the 5 water molecules are added to this CuSO4, which was blue in color. But out of those 5 molecules of water, one water molecule which is outside the bracket. Now where is the outside the bracket? You can see here I am talking about this. So when you look into this area, or when you look at the structure of CuSO4 into 5H2O, this is your CuSO4 into 5H2O, the CuSO4 into 5H2O, this is what we have. This, out of this 5 water molecule, one water molecule is here, whereas four water molecules are inside the bracket. So we are talking about these one water molecules. Only one water molecule which is outside the bracket, that is the coordination sphere, is hydrogen bonded. The other 4 molecules are coordinated. You can see here that in CuSO4, these 4 water molecules, my dear students, are actually coordinated, whereas this one water molecule is actually the hydrogen bonded water molecule. So you can see that water molecules can be added in a 3 different way. Either they are coordinated, or they can be added as an interstitial water molecules, or they can be added as a both, either coordinated or in the form of the hydrogen bonded water. Now let's move and understand the next part of this chapter. So what is there in the next part? Hard water and soft water. My dear students, we have seen that hydrogen has got its isotope, which is known as the deuterium. So if you have H2O, instead of H2O, if you have D2O, then this is what it is known as the hard water. So no, my dear students, it is known as the heavy water. Actually, I have made a mistake. This is what it is known as the heavy water. Heavy, heavy water. But hard water is something else. So let us find out what is hard water and why it is of our interest, or why do we want to study about the hard water. So let us study. Presence of calcium and magnesium salt in the form of their hydrogen carbonate, chloride and sulfate in water. Now what is the meaning of in water? Means dissolved in water. Dissolved in water. So please remember, my dear students, that if we have calcium hydrogen carbonate, CaHCO3 twice, or if we have magnesium hydrogen carbonate, MgHCO3 twice, or if we have CaCl2, or if we have MgCl2, or if we have CaSO4, or if we have MgSO4, these all 6 salts, they are actually water soluble. They can be easily dissolved in water. And when they are dissolved in water, the water looks like a pure water. But this water have the salts of magnesium plus 2 and calcium plus 2. And this salt may be hydrogen carbonate salt of calcium and magnesium. They can be chloride of calcium, magnesium. They can be sulfate of calcium and magnesium. And they are present inside the water as a dissolved salt. If these 6 salts are, or these 6 salts together, or any one of them at least, remains present in water as a dissolved salt, then such salt is known as the hard water. Please remember, my dear students, if the salts like the salts of calcium and magnesium, they may be the hydrogen carbonate salt, chloride salt, or sulfate salts. If any one of them at least, or all these salts, or more than one salt, if they are remain present into the water, this water behaves like a hard water and it has got some different properties. Let us study about the properties of hard water and how can make the hard water soft water. This hard water does not give lather with the soaps. So you can see that this hard water which contain the calcium and magnesium salts, it reacts with the soap. These soaps are soap that containing the sodium stearate, that is C17H35COO. This part is your stearate, and if you put H after it, it becomes stearic acid. And sodium stearate means instead of hydrogen, the sodium is being added. So this is the sodium stearate, which is known as the soap, that reacts with the M plus 2 ions. They may be calcium plus 2 or magnesium plus 2 ion, and they form the calcium stearate or calcium stearate or magnesium stearate. That means they may have the compound like C17H35COO twice calcium, that is calcium stearate, or they may have C17H35COO twice Mg, that is magnesium stearate. This, either of this compound, if it is present, this compound is known as scum. So this compound, if it is produced, it is known as scum, where M is calcium or magnesium, and these sodium ions are being produced. So my dear students, when this soap reacts with the hard water, because hard water has got calcium and magnesium salts, when this soap reacts with the hard water, it produces scum, and thus the soap is being wasted. The soap is being wasted. And it does not actually clean the substances that we want to use it for cleaning purpose. So then what is soft water? Water free from soluble salts of calcium and magnesium is called soft water. If the water does not have any calcium or magnesium salts present into it, we call it as a soft water. Soft water give lather with the soap easily, because soap does not produce scum. It gives lather with the soap. Hard water forms scum and or precipitates with the soap. So hard water is unsuitable for laundry. We cannot use it for washing the clothes, and it is harmful for boilers. So the question you may be asked, that why hard water is not suitable for the boilers. So let us understand the reason that why we should not use hard water for the boilers. So we have a question. How hard water is harmful for the boilers? Hard water has calcium or magnesium sulfates, chlorides, or hydrogen carbonates. That is why these salts dissolves in this water. Now in boilers, these salts are deposited in the form of scale. So when we heat the water evaporates, and these salts, they are deposited in the boiler in the form of scale. This scale reduces the efficiency of the boilers, and that is why these scales, or the deposition of the salt, which is known as the scale, that decreases the efficiency of the boilers, and that is how these salts are harmful for the boilers. Now we want to study about the various types of hardness. So hardness is of two types, my dear students. The first type of hardness is known as the temporary hardness. Temporary hardness is due to the presence of magnesium and calcium hydrogen carbonate. Please remember that temporary hardness is due to the presence of magnesium and calcium hydrogen carbonate. Temporary hardness can be removed by two different methods. So first we will study the first method of removing the temporary hardness, and that is what it is known as boiling. During boiling, soluble magnesium hydrogen carbonate salt is converted to insoluble, means not soluble magnesium hydroxide salt, and thus soluble calcium hydrogen carbonate are converted to the calcium carbonate, which are insoluble. So magnesium hydrogen carbonate is converted to magnesium hydroxide. Calcium hydrogen carbonate, which were soluble, they are converted into insoluble calcium carbonate salts, and then by filtration they can be easily removed. So by the process of filtration, it is because of the high solubility product of the magnesium hydroxide as compared to the magnesium carbonate that magnesium hydroxide is precipitated. These magnesium hydroxide precipitates can be removed by the filtration process, and thus we can get the soft water. Now here I have given you some important information, my dear students, so that you can understand this process. A magnesium carbonate, they have KSP, that determines their solubility, and this value is 6.8 into 10 to the power minus 8. But when you look at the magnesium hydroxide, its KSP is 1.8 into 10 to the power minus 11. So this value is less than this value. And that is why the KSP value for magnesium hydroxide is less than the KSP value of magnesium carbonate. MgOH is by far less soluble than magnesium carbonate. So magnesium carbonate is very much soluble in water, whereas magnesium hydroxide is less soluble in water. Solubility product of magnesium hydroxide is smaller than the solubility product or KSP of magnesium carbonate, indicating lower solubility of magnesium hydroxide. So my dear students, when we look at these reactions, what happens when calcium hydrogen carbonate is heated, we get calcium carbonate, water and carbon dioxide. So when we should heat magnesium hydrogen carbonate, actually we should get magnesium carbonate, H2O and CO2. But we do not get this magnesium carbonate MgCO3, we do not get MgCO3 because actually the MgCO3 remains as a dissolved salt into the water. But this magnesium hydroxide, which is produced by the reaction of Mg plus 2 and OH minus present into the aqueous solution of our magnesium hydroxide, and thus this magnesium hydroxide is precipitated instead of magnesium carbonate. So here, my dear students, when we heat magnesium hydrogen carbonate, instead of production of the magnesium carbonate MgCO3, here we get magnesium hydroxide produced, and this magnesium hydroxide is precipitated. So all the magnesium ion present, they are precipitated as a magnesium hydroxide instead of magnesium carbonate. Please remember, this is the last time, when magnesium hydrogen carbonate is heated, instead of magnesium plus 2 ions, that can be precipitated as a magnesium carbonate, but the solubility of magnesium carbonate is more than the solubility of magnesium hydroxides. So all the magnesium hydroxide, they combine with the OH minus ion present into the water, and they are precipitated as a magnesium hydroxide instead of magnesium carbonate. And if some magnesium carbonate is produced, it remains dissolved into the aqueous solution. And thus by filtration, these two salts, magnesium hydroxide or calcium carbonate, they can be removed from the water, and thus the temporary hardness of water can be removed by just boiling. Now we have the second method, which is known as the removing temporary hardness of water by Clark's method. In this method, a calculated amount of lime, that is calcium oxide, is added to hard water. It precipitates out as a calcium carbonate and magnesium carbonate and magnesium ion. Let us see how does it work. So when we add the lime, my dear students, into the water, magnesium hydroxide which can be filtered out. When we add lime to the water, it produces calcium hydroxide. This calcium hydroxide which is produced into the water, it reacts with the calcium hydrogen carbonate and magnesium hydrogen carbonate, which causes the temporary hardness of water. So this magnesium hydrogen carbonate or calcium hydrogen carbonate, which are responsible for the temporary hardness of water, they react with calcium hydroxide, which is produced by the reaction of lime with water. Thus, by these two reactions, calcium hydrogen carbonate are converted to insoluble calcium carbonate and magnesium hydrogen carbonate are converted to magnesium hydroxide, which is insoluble, and some part of the calcium carbonate may also be precipitated. All this calcium carbonate and magnesium hydroxide, they can be filtered by the process of filtration, and this is how, as a filtrate, we get the soft water. So after filtration, whatever the filtrate we get, whatever the water we get, it is soft water. Now, my dear students, we want to study about the permanent hardness. So as we have seen that hydrogen carbonate salts, they give the temporary hardness. That means chloride salts and sulfate salts must be giving you the permanent hardness. So permanent hardness is due to the presence of soluble salts of magnesium and calcium in the form of the chlorides and sulfates. So if you have calcium chloride, magnesium chloride or calcium sulfate, magnesium sulfate present in water, this water contains the permanent hardness. Permanent hardness can be removed by boiling, permanent cannot be removed by boiling. So please remember that when we boil the water, the permanent hardness cannot be removed. Permanent hardness can be removed by the following methods. Let us study the first method. Method number one, treatment with the washing soda or sodium carbonate. Washing soda reacts with the soluble calcium and magnesium chlorides and sulfates in the hard water to form insoluble carbonates. So you can see, my dear students, then we have MCl2 or MSO4. This MCl2 may be CaCl2 or MgCl2. This MSO4 may be CaSO4 or MgSO4. When they react with the washing soda Na2CO3, calcium, they are precipitated as MCO3 and NaCl or Na2SO4 are being produced. Thus, this MCO3 may be calcium carbonate or magnesium carbonate. So, the calcium carbonate and magnesium carbonate are precipitated. These precipitates may be filtered, and the filtrate we get is your soft water. Then we have the next method, which is known as the Kalgan's method. There is a compound, its name is the sodium hexametaphosphate Na6P6O18. Sodium hexametaphosphate. Sodium hexametaphosphate, commercially it is known as the Kalgan. So by using the Kalgan's method, we can remove, or using this Kalgan, sodium hexametaphosphate, we can remove the permanent hardness of water. When this Kalgan is added to the hard water, following reaction takes place. Let us see. This hexametaphosphate is turned into 2Na plus ion and Na4P6O18 minus ion. Here your M is magnesium or calcium. This magnesium or calcium plus 2 ions, when they react with this hexametaphosphate, this hexametaphosphate ion, they trap this calcium or magnesium ion by making a complex compound. This complex compound is Na3MP6O18. So these M plus 2 ions, they are trapped into a complex compound, and sodium ions are also produced. As this Kalgan traps these magnesium and calcium ions into a complex compound, the permanent hardness of water can be removed. The complex ion keeps the magnesium and calcium ions in the solution, and the permanent hardness is removed. Now next method, which is known as the ion exchange method, which is the third method. This method is also called the zeolite or permutate method. Please remember, my dear students, that this ion exchange method is also known as the zeolite or permutate method. Hydrated sodium aluminum silicate. Now please remember this sodium aluminum silicate. Remember that this sodium aluminum silicate is also known as the zeolite. So this zeolite is nothing but zeolites are the sodium aluminum silicate or sodium aluminosilicate. This is how you call. So hydrated sodium aluminosilicate, which is also known as the zeolite or permanent. For the sake of simplicity, sodium aluminosilicate NaAlSiO4 can be written as NaZ. That means AlSiO4 minus 3 is written as Z. So we, for simplicity, we will write it as NaZ. Where this is added in water, the, the exchange reaction takes place. So my dear students, when this NaZ is added to M plus water containing M plus 2 ion, this M plus 2 ion forms Mz2 and sodium ion are being removed. So these aluminosilicate ions again trap the M plus 2, that is calcium and magnesium plus 2 ions into the solution, and thus they remove the permanent hardness of the water. So these sodium aluminosilicate or zeolites, they react with the calcium and magnesium ion, and they again form aluminosilicates of the calcium and magnesium, and thus they remove the calcium and magnesium ions to come in contact with the sulfate and chlorides, and thus these salts are being removed, or these calcium and magnesium plus 2 ion, they cannot show their effect, and that is why the permanent hardness of water is being removed. Permanent or zeolite is said to be exhausted when all the sodium ions are used up. So whatever the amount of zeolite or permanent that we have added to water, when all they loses their Na plus 2 ions, we say that the zeolites are being used up. Then these zeolites, they can be regenerated further by treating them with the sodium chloride. So these zeolite, we take them out in the form of Mz2. They are allowed to again react with the sodium chloride, which is common salt, and again they give NaZ. This NaZ is nothing but your sodium aluminosilicate, and again this NaZ, zeolite or permanent, they can be reused, my dear students. And that is why we use the word regenerated. Regenerated means they are converted back to their original position, and they are again used to remove the permanent hardness of water. Now, my dear students, we want to study about the last method, which is known as the synthetic resin methods. These resins are the carbon compounds or organic compounds, my dear students, and they are produced by the human being. That is why they are known as the synthetic resins. Nowadays, hard water is softened by using the synthetic cation exchangers. So let us see how these synthetic cation exchangers work. This method is more efficient than the zeolite process. First, we will study about the cation exchange resins. So these cation exchange resins contain large organic molecule with SO3H functional group and are water insoluble. They does not, or they do not dissolve in water. Ion exchange resin, that is RSO3, is changed to RNA by treating it with the NaCl. You can see, my dear students, if you have resin, this resin, when it reacts with the NaCl, it produces RNA, that is the sodium salt of resin, HCl minus and HSO3 plus. The resin exchanges Na plus ions with the Ca plus 2 ion and Mg plus 2 ion present in the hard water and make the water soft. Here R represents the resin. So, my dear students, this resin, which is known as the RNA, I'll explain you. This RNA, the Ca plus 2 ions or Mg plus 2 ion, if they are present, this turns out to be R2Ca. When it reacts with the Ca plus 2 or Mg plus 2 ion, it turns out to be R2Ca and produce 2Na plus. Same way, if we have 2 RNA, if they react with Mg plus 2 ions, they again produce R2Mg and 2Na plus ions are being produced. So this is what it is, the exchange of ions. These ions which are present as a Ca plus 2 or Mg plus 2 in water, they are exchanged in the form, they are exchanged in the exchange with the sodium ions, and thus the resins combines with the Ca plus 2 and Mg plus 2 ions. That is what they try to tell you into this paragraph. The resin exchange Na plus ions with Ca plus 2 and Mg plus 2 ions present in hard water and thus removes the hardness of water. There is, yes, I have shown this reaction to you even, that RNA, when it reacts with M plus 2 ion, it produces R2M and they produce sodium plus ion. The resin can be regenerated by adding them into the sodium chloride. That is what we have seen, that they can be again regenerated. So if you have R2M and if you allow them to react with the 2NaCl, you can easily produce 2RNA and MCl2. So this is how this RNA can be regenerated by allowing them this R2M resin to react with the sodium chloride NaCl. Now, my dear students, instead of converting this RSO3H to RSO3Na, we can directly use them as an RH. So instead of RSO3H, now we will use the word RH. So if we have RH, this RH is used as a cation exchange reagent. So suppose we use RH and allow them to react with the calcium plus 2 ion or Mg plus 2 ion, they again gives us R2M and 2H plus. Due to the production of this H plus, instead of Na plus, my dear students, here only H plus is being produced. So due to the production of H plus, water become acidic. So instead of RNA, my dear students, instead of RNA, resin or sodium resin, if we use the hydrogen resin only, then this resin also exchange the magnesium and calcium plus 2 ion, but here the water or here the hydrogen ion H plus ions are produced, and that is why the water become acidic. Now we cannot use this acidic water, and that is why we have to pass this acidic water through the anion exchange resin. So during the cation exchange process, H plus is exchanged with the Na plus, Ca plus 2, Mg plus 2 ion or any other ion present in the water, which ultimately produces H plus ions and acidic water is formed. This acidic water has to be passed through the anion exchange resin. So please remember that if we use RNA or resin, sodium salt of resin, we need not to pass it through the anion exchange resin. But instead of simple RNA, if we use simple RH resin, then after passing through the cationic resin, we need to pass the water through the anion exchange resin too. So now the first part we have done, we have passed the water through the cation exchange resin which we have used as RH. Now we are going to use it for the anion exchange resin. Now what are the anion exchange resin? These RNH2 containing NH2 group are called the anion exchange resins. These anion exchange resins, when they are added to water, they produces RNH3 plus and OH minus. This RNH3 plus OH minus is a anion exchange resin, and that produces OH minus ion when the water is passed through it. So let us see how does this anion exchange resin work. This anion exchange resin reacts with the X minus ion present into the hard water, and then they exchange this X minus ion resin and produces OH minus ion. This X minus it may be your Cl minus ion or HCO3 minus ion. Suppose if you have sulfate ion, so for sulfate ion we can write 2 RNH3 plus OH minus and SO4 minus 2, which gives us RNH3 twice SO4 and 2 OH minus. So now the acidic water is passed through the anion exchange resin and we get OH minus ion produced. So pure demineralized or deionized water free from all soluble mineral salt is obtained by passing water successively through the cation exchange resin and then after cation exchange resin by passing it through the anion exchange resin. After each pass with cation exchange resin, we get H plus ion, and for each pass of anion exchange resin, we get OH minus ions. These OH minus ions and H minus ions, both H plus ions and OH minus ions neutralize themselves to produce water, and thus we get the demineralized, deionized water. Please remember that by the passing water through the cation exchange resin RH and the anion exchange resin RNH2, we get a demineralized, deionized water. These resins, The exhausted cation and anion exchange regimes can be regenerated. How do we regenerate them? There is a process. For regeneration, cation exchange regimes are treated with the dilute acids, and anion exchange regimes are treated with the dilute alkali. Dilute acid cation exchange regimes, my dear students, uh, these cation exchange regimes are turned out to be, let us see what they are turned out to be. So these cation exchange regimes are turned out at the end of the process when they produces H plus ion, they are turned out to be R2M. And anion exchange regimes, my dear students, these anion exchange regimes, they are turned out to be RNH3 plus X minus. So if we have RNH3 plus X minus or RNH3 twice SO4, if we allow them to react with, suppose let us say NaOH, which is an alkali, what happens? We get RNH2, we get NaX, and we get this Na